So now let's talk about some applications of Gauss's theorem. So the first application I want to talk about is from electromagnetism. So let's think about the magnetic field B and electric field E for a second, just as an idea. So electric field E comes from a charge, and it is possible to have a net charge at a single point. Just say, here's a charge. So an electric field may have source points. When you have a charge, that is like a source point for an electric field. So another way to say that in math is that you could have divergence of E not equal to 0. That's a source point. It comes from the charge. Okay, now magnetic fields. Magnetic fields, if you don't know, are caused by north and south poles, and that's what creates the magnetic field lines. Now they always come in pairs. It is not possible to have net magnetism at a single point. That's called a monopole. So in other words, the divergence of B must be equal to 0. So this is just a fact from physics. It's also called Gauss's law for magnetism. Now, what if we take the fact that divergence of B being the electromagnetic field, must be 0, and let's apply Gauss's theorem. So what does Gauss's theorem tell us? We know that so if divergence of B is 0, take the triple integral. So the triple integral of the divergence of B must be 0 because of the triple integral of 0. But by Gauss's theorem, that tells us that it's the double integral over the surface of B dot ds, where, as always, the surface S is the boundary of the solid B. So in other words, for a magnetic field, flux over a closed surface is always 0. And that's another form for Gauss's law for magnetism. And this is also one of Maxwell's equations, and that forms the foundation of classical electromagnetism. So for this class, I don't necessarily expect you to understand the physics, but given the statement div B equals 0, look what we can conclude from that. That also tells us that the triple integral of the divergence must be 0, therefore the flux integral must also be 0. And then in a physics class, you can interpret the physics meaning for that. So there's one way that we can use Gauss's theorem to get some implications. Okay. So I think I'm gonna skip this one for now, and let's talk, oops, here we go. Okay, so I'm gonna work through this example because it's gonna bring us to a nice point. Okay, so Gauss's theorem applies not only to simple solids, but also unions and differences of the solids. So we get there by adding and subtracting. So how are we going to use this? So what does this mean? Suppose a three-dimensional solid, which I'm going to call B1, is completely contained in another solid, which I'm going to call B2. So if you like, imagine one ball inside another ball. And so B1 has boundary, which is a surface S1, and that's got outward normal N1. Okay, and again, that's completely inside the other one. So your outside solid B2 has boundary surface S2, and that has outward unit normal N2. Okay, so if it helps, just imagine one solid here, but then there's another solid that is outside that, and it's filled in, but I don't want to fill it in too much. Okay, so inside is number 1, and outside is number 2. Now, we're going to talk about the solid that is between them. So if you like B2 minus B1, actually, I'm going to label that as B. So B is the solid that is between them. Okay. So now let's apply Gauss's theorem and see what happens. So the triple integral over B2, which is the entire thing, of the divergence of f dv is just split up B2 into its two parts. Its inside part is B1, and then the sort of between part is B. So that gives you the sum of those two triple integrals. Now, by Gauss's theorem, we know that the first one, the first integral on the left side, we can just rewrite that as a surface integral. And the second one, we can rewrite that as a surface integral. Okay, now why would we do this? We're about to use this for something. And also we're leaving the third integral as a triple integral on purpose. And the question is why? If vector field F is undefined at a point in B1, which is the inside bit, actually, let me just expand this, hold on. Okay. Then we cannot calculate the divergence in B1. However, we can get, so we wouldn't be able to write down that first line before getting the second equation. But we can get it another way. So for the between solid B, note that if we want to have outward normals, the outward normal N2 is still pointing outward. Let me use my graph for a second. However, the outward normal for B on the inside has to point inward. Sorry, there's a lot of lines going on there. So here's S1, but relative to B, which is this in-between thing, an outward normal would point in that direction. Outward from B has to point in that direction, which relative to B1 is pointing inward. So you get that its normal is N2, but then on the outside, but then negative N1 on the inside. So putting that all together, we get exactly the same statement using Gauss's theorem. So the triple integral over B, the between solid, of divergence of f dv is, by Gauss's theorem, the double integral of the surface of f dot ds, which of course is the double integral of the surface of f dot unit normal n ds. Break that up into the two surfaces, so two separate integrals. And then on S1, your normal is negative N1 because now it must be pointing outward relative to B, which was inward relative to B1. And on S2, it's still regular N2. And then finally, you just get the difference of the two. And then one of them is negative, and then that winds up being equivalent to the equation that we had before right here. Okay, there's two ways to get to that equation. This is the equation that we want. Why is that the equation that we want? We want to talk about things where it's going to be undefined where the vector field is going to be undefined at a certain point. And we want to avoid that point. Let's take a look what that means. Our next application is electromagnetism. So we know the formula for the electric field, E equals KQ over R cubed times vector R. Show that the flux through any surface enclosing the charge Q at the origin is 4 pi KQ. So remember that we did this previously for a sphere. Now we're going to generalize it to any surface. So we cannot calculate the surface integral because it could be any surface, so we don't have the formula. Also, we can't use Gauss's theorem and just calculate the divergence over the entire solid because the field is undefined at the origin, because at that point R equals 0 and you can't divide by 0. So we're going to overcome both of these problems by using the thing that we just did. We're going to split it into two pieces. So we're going to split into two pieces looking like this. We're going to split it into one piece where we can calculate the surface integral and another piece where we can calculate the divergence. Okay, so how does that work in this case? So we're going to make our inside piece a solid ball whose surface will be, of course, a sphere. And then the outside piece will just be the rest. Okay. So by the previous result, here's what we want. So we get that. The triple integral over the entire solid is the same as the double integral over the surface of the vector field .ds. Now, we just saw, the last thing we proved, is that this is just negative of the double integral over the first surface, the inside surface, plus the double integral over the second surface, which is the outside surface. That was the thing that we proved using Gauss's theorem a second ago. So let's figure out what this, now we can, there's things here that we can calculate. So what is the divergence of E? Well, we have to write out E by the components. So notice that it's that, the vector field is that constant times position vector R is just x comma y comma z. So the first component is x over r cubed. Second component is y over r cubed. Third component is z over r cubed. So we take the partials of each of those and then add them up. So when you do that, you get this expression. And remember, we're using the fact that r is the square root of x squared plus y squared plus z squared. Okay. So now, sorry, that's before taking the partials. After taking the partials, you get this long thing. Excuse me. Okay. So doing a bit of algebra and working it all out, this actually simplifies to the following thing. 3r to the negative 3 minus r to the negative 5 times 3x squared plus 3y squared plus 3z squared, which of course is just 3r to the negative 3. And look at that, it cancels. So the divergence of E is just 0, as long as r is not 0 is defined. So knowing that, that tells us that the two surface integrals, since the divergence is 0, we can solve it around, and therefore we know 0 equals negative of the first double integral plus the second double integral. Therefore, double integral over S2 E dot d to the s equals double integral over S1 of E dot ds. So we previously, so remember S1 was any surface that we wanted to make, and we made it a sphere. Now we've previously calculated the flux for a sphere with charge Q inside. So there's a shortcut method, there's another shortcut method here, which I'll just put up on the screen, but I'm going to skip that and I'll just go right to the result, which we had previously. You can look at the shortcut method on your own if you like. So the result, which we previously calculated, is that the flux for the electric flux for a sphere with charge Q inside is just 4 pi k Q. And K, by the way, is a known constant from physics, looking like this. So notice what we have proved. We've proved that it didn't matter what the outer surface was. The total flux is going to be basically 4 pi kq plus 0, or in other words, it'll be 4 pi kq. And so by knowing what the constants are, we can then turn this around and say that the flux double integral of over the surface of E dot ds is just Q. Another way to write the constant is Q over this thing epsilon 0. And this is Gauss's law for electric fields, and this is also one of Maxwell's equations. Now we can express this another way. So another way to think of the charge is that if you think of the charge density, which is charge per unit volume, the charge just comes from doing the triple integral of the density dV over your three-dimensional solid region B. So knowing that, we can say that since Q is, we can now rewrite Q, our total charge, as this triple integral of the density. We can now write that double integral over the surface of U dot ds equals, re-express Q, 1 over epsilon 0 times the triple integral over your solid region B of density, charge density P dV. But remember, this is Gauss's theorem. We can apply Gauss's theorem. Gauss's theorem means, therefore, that this must be the triple integral of the divergence. So that means that P, your charge density, must be the divergence of E, and then including the constant. So the divergence of E must be P, the charge density, divided by the constant E0. And this is Gauss's law for electric fields. Now it's written using derivatives, and I say derivatives because remember, divergence is calculated using derivatives. Okay, one final comment. We've previously shown that the electric field E is conservative, which means that it's the gradient of some function f. So it can be written as fx, comma fy, comma fz. Now remember what divergence is. Divergence is basically gradient operator dot the vector field. So in other words, divergence of E is just the divergence of the gradient of your function f, which when you calculate it out means you wind up with fxx plus fyy plus fzz. Now another notation for this is we write like div is grad dot, and grad is just grad, so it looks like grad dot grad f. This is often written as grad squared of f. And then another notation for that is we turn the grad upside down and it becomes a triangle. So triangle of f is another way to write down this expression. So this triangle is called the Laplacian operator, and Laplacian of f equals 0 is called Laplace's equation. And this is a very, very, very important equation in advanced mathematics and physics. It comes up all the time. Okay. So those were a couple of applications where Gauss's theorem came up. Okay, so let's get into some more applications of Gauss's theorem. Next one I want to look at is the area of magnetism. So from physics, we learned that there's a relationship between the current density, which is J, and the magnetic field, which is B, as long as we assume that there's static charge, meaning the charge is not in motion. So we have that J equals M0 times the curl of B. And M0 is a known constant. It's C over 4 pi, which is approximately 14,801. Okay, so, and I'll just say, physics facts, this is the static version of Ampere's law, which is one of Maxwell's equations. Okay, so there's the background equation. There's the equation that we need with a little bit of background physics. So now we ask the question, what is the total current? And current is the flux of J, because we're integrating the current density, if we take our surface to be a sphere. Let's take a look. So we know that the flux is just the double integral over the surface of j dot ds. And we know that j, by the given thing, should be m0 times the curl. Let's just stick that in there right there. So it's a constant. Okay. But from here, we can apply Gauss's theorem. So Gauss's theorem, we know how to rewrite the double integral over the surface. It's just the triple integral over the three-dimensional solid of the divergence of the vector field. That's just the divergence of the curl of B dV. Using our constants. Okay. But now we apply one of our known facts about vector field operators. The divergence of the curl of a vector field is just 0. So therefore, the triple integral is just 0. And so we know, now let's go back and figure out what we make a conclusion. This tells us that in general, the current due to a magnetic field over a closed surface is always 0. Okay. Let's do another application. Next application is in the area of thermodynamics. Okay, so here's the setup. Recall that the heat conduction field for temperature T is vector field F equals negative some constant K times the gradient of T. And the heat flux of T across the surface S is just the double integral over the surface of the vector field dot ds. And then plugging in for the vector field, it's just negative K times the double integral of the surface of the gradient of T dot ds. So now let's apply this to a question. If S is a closed surface and T is the temperature function is this, z plus 3xy plus 8 minus 4y plus xyz, what is the heat flux across S? So let's set it up. Note the heat flux is just the flux integral. So negative K, constant pulled out, double integral over the surface, gradient of T dot ds. But we know that by Gauss's theorem, this is just negative K times the triple integral over the solid of the divergence of the field. So the divergence of grad T dV. Let's calculate divergence of, the divergence of the gradient of T. So in this case, the gradient of T is 3y plus yz, comma 3x minus 4 plus xz, comma 1 plus xy. And when you calculate the divergence of that, you get 0 plus 0 plus 0 equals 0. So in this particular case, with this particular function, the heat flux of T across S is 0. So this is a case where Gauss's theorem greatly simplifies our calculation. Now, it's not always true that it's going to be 0, but it is for this particular function. And those are some applications of Gauss's theorem. Let's just make some statements in physics in different areas.